Okay, we're back and we're doing some magnetism. In particular, we're going to focus on this so-called Lorentz force, the F equals QV cross V. This says that when a charged particle comes flying into a magnetic field, you have this cross product, and that cross product vector is the force vector that the charged particle feels. Now, there's a really important application of this force and this phenomenon called a mass spectrometer. Sometimes you hear about this in chemistry because chemists have actually used this to determine what type of atom or molecule they're dealing with. And the principle, it's actually fairly simple and straightforward. Basically, you ionize an atom, and this allows you to figure out what the charge is. You kind of know what that is. You send it through a device which I'm going to outline in a second called a velocity selector. Okay, basically it's a combination of electric fields and magnetic fields which allows you to figure out very precisely what the speed of this ion is. That ion then flies, after the velocity selector, goes into a region where you have only a magnetic field, and when a charged particle flies in a magnetic field and feels this cross product force, you get circular motion, okay, which we'll discuss in a second. And nowadays, with fancy electronics and these devices, we can measure the radius of curvature pretty accurately as well, and we'll figure out how you can determine the mass of that particular atom, okay, that ion that came flying into your device. So a very crude sketch, as you can see. Basically, you have a particle over here. Let's say it's a positive charge, which is flying in with some initial speed, and it goes between two plates, kind of like a parallel plate capacitor, which is hooked up to a battery. And in this case, if you look at the orientation, the positive plate is down here at the bottom, and the top plate will be have a negative charge. So that means you have an electric field, which I'm drawing in blue here. And because you have plates, it's a uniform field. So we can determine how strong that electric field is. Okay, basically, in not worrying about signs or anything, electric field is a change in voltage over a change in distance. So if we know the distance between those plates, it's just going to be whatever that voltage difference is of your battery divided by the distance between the plates. It's a constant force. Now, when a positive particle is inside that region, inside an electric field pointing upwards, it's going to feel an electric force pointing upwards. Okay, so if that's all we had, this thing would basically go into projectile motion, and it would crash into the plate on the upside. However, what I also drew here are all these dots, which represents a magnetic field. So this parallel plate capacitor is in a magnetic field, and if I draw the force diagram of our particle, we know we have this electric force going upwards. And in a velocity selector, what your goal is, basically, is you want this particle to fly straight through. Okay, you don't want it to get deflected by either the magnetic force or the electric force. So your goal is you want these two forces to be equal and opposite to each other. So that means if you want a magnetic force to go down on a positive particle, you need a magnetic field to come out of the screen, out of the page. You can do the right-hand rule, QV cross B. If you point your right thumb to the right, that's the direction of motion, that's the velocity. You want your index finger to come out of the screen. Okay, that's the magnetic field. And then your middle finger will be the force, and it should be pointing downward. Now the magnitude of that magnetic force, okay, so this is our goal. We want those two forces to be equal to each other in a velocity selector. The magnetic force is charge times speed times the strength of your magnetic field. And in this case, because it's a cross product, you also need a sine of some angle. Okay, the angle between your velocity and magnetic field, in this case it's 90 degrees. And you want that to be equal to your electric force pointing upwards. Okay, and that's charge times electric field. That's how you find electric force. So notice that the charge drops out. And what we do is we solve for speed. We solve for that velocity. And when you do that, it's the strength of your electric field divided by the strength of your magnetic field. So in other words, any ion that comes flying into this region of both the magnetic field and electric field, going this speed, won't get deflected by either force, and it flies straight through. So generally what you would do in a velocity selector is you have like a wall over on the right edge of these plates and with a little hole in it. And so only those particles with that speed going straight can pass through. Now it flies into the region where you've left the plates, you've left the electric field, and it's just magnetism. So when it flies in there, it now feels just the magnetic force going down, which means it's going to fly into a circle that's downward. So this would be the trajectory, the path that our positive ion takes. And what you can do in devices is you can measure what the radius of that circle is pretty accurately. So now, because you're in a circle, you have centripetal force, mv squared over r. And why does it go in a circle? Well, it goes in a circle because of this magnetic force. Okay, so one of the v's drops out, and what you can do is you can solve for the mass. So it's the charge of your ion, the number of Teslas, okay, the strength of your magnetic field, which you have control over, especially if you're using an electromagnet, which is pretty typical. You measure the radius, and then you can divide by the speed. But we know the speed from the velocity selector, so if we substitute this in, we get a final expression for the mass of our ion. We have the charge times magnetic field times radius all over our velocity. And if we simplify this, the magnetic field slips up. You have magnetic field squared times the radius of your circle all over the electric field. And again, you know the electric field if you know the voltage and the distance between the plates. So you could substitute that in if you wanted. Okay, so this is where it's at. This is coming from our QV cross B. It's combining it with some mechanics, okay, centripetal force. And you can plug in your measurements, you can plug in these values, and you can determine the mass. Now this is kind of cool because mass spectrometers are what were used to find isotopes. You'd have ions of the same element flying through. It would have the same charge, it would have the same magnetic field, you could have the same electric field, but you would have like, maybe 2 or 3 different tracks, two or three different radii, even if you had the same sample, let's say carbon. Well, when you solve for these masses, one of the mass solutions that you get would be carbon-14, let's say, in addition to the normal carbon-12. So that radioactive isotope of carbon can be found using these mass spectrometers. Okay, so it's a neat, kind of combining a few different ideas. We're combining some electricity, okay, this electric force, charge times electric field. We're using voltage differences and distance of capacitors to determine the strength of the electric field. And we're combining that with this new thing, this QV cross B idea, okay, the magnetic force, and the fact that these things fly in circles. And we've got ourselves a very useful contraption. Okay, this is pretty typical. We'll do lots of different sample problems and have other applications of this sort of thing. So until next time, we'll see you later.